Good afternoon, everybody, and thanks for attending this June lecture from Trygve Espeland of ESNA Naval Architects in Norway. Trygve is going to give us a presentation of around half an hour on SES opportunities in the energy transition. And I'd like to hand over to you straight away, Trygve, to introduce yourself and tell us all about the opportunities.
Thank you, Alan, and thank you for the opportunity to present a little bit on what we are doing. I was quite happy that we managed to find a title which basically summarized everything we do at job. So I had to break it a bit down to find kind of summarize it. But this is kind of the what we see is a lot of opportunities, and we see and hope for a bright future for the SES. In the presentation here on the first slide, just to briefly tell you that those are two vessels that have been designed by ESNA. On the right hand side, we have the Sea Puffin 1, which is a daughter craft. It's designed for offshore wind. There's a very small hook on top here, so she can be hoisted on board a mother ship. On the left-hand side, we have the Sea Wind Pioneer, which is a diesel-electric crew transfer vessel built at White Shipyard on Isle of Wight. ESNA, we are a ship design company. Many of you, I think, know near Skomedal from before. But basically, we have spent our career and work on figuring out how to make sense of an SES. We established ESNA in 2015, and we took this title as the world leading independent design house because that title was available. But it's also kind of summarize why we like this, because we bring something that most people doesn't know. So it's quite exciting to work with end clients. We are a small, flexible company. I like to work like that and being in charge of what I do. And being small and finding these opportunities, we need to work closely with end clients like wind farm owners or people like Rome who has a lot of experience with oil and gas crew transfer vessels. And we work also very closely with suppliers. Myself, I'm a naval architect who studied in Trondheim and on the university there. My master degrees was titled Simulations of SES. I basically studied SES and been working with it ever since. So as I said, the SES among you guys, it's quite well-known stuff. But among most people and most yards, it's fairly unknown. Most people have never heard about an SES. So the business idea is around complementing a yard. So principally, we design vessels as naval architects. We also design the equipment packages like the lift fans or find suppliers of lift fans. We design the motion damping systems. And the idea is that we supplement the yard so that we can work with any yard worldwide and together construct and build an SES. That is kind of the opportunity we found that this is something that isn't offered by anybody else. We focus on the SES, which is the vessel we know, which gives us very good energy efficiency. And we really like new technology. We are engineers, and we like what's going on and figuring it out and try to make sense of it. And what we have seen is that, especially with new technologies and especially electrification, there is a lot of benefits with the SES. We established the company in 2015, and the first thing we did was actually to make the SES motion damping system electric. So in 2016, we had the first testing of this motion damping system in a university here in Norway. Focusing on the title with energy transition, it's hard to avoid the electrification. Just giving an example picture here. This is again the Sea Puffin 1. And yeah, these curves are everywhere. I just took one random, but there are a lot of things going on within offshore wind. There is a lot of construction all over the world, and these require new type of vessels, which gives a lot of nice opportunities and work for us. So there is, combined with this, there are a lot of new requirements like UN's sustainable goals and the EU taxonomy rules coming. And there are a lot of ambitious companies. I just took Ørsted like an example here, but they are saying that basically the vessels they charter in 2040, they will not charter a vessel that is running on fossil fuels. Yeah, most people see this as requirements, but I see them as opportunities, of course. There's a lot of things to think of. And I think a main summary of the energy transition is that it's quite dramatic. It's a huge change. You kind of compare it with going from sailboats to kind of oil or coal-powered vessels, but it's not that simple actually, because it's going from oil. This is from the DNV outlook, transition outlook last year, but it shows it quite nicely because most vessels runs on some kind of oil, heavy oil or diesel fuel or whatever. And what's coming next is not changing from one fuel to another, but it's changing to a lot of different fuels. And there's a lot of different type of fuels with a lot of different properties. Something is well suited for larger vessels, something for smaller vessels. And what DNV thinks is in their kind of crystal ball here is that in principle, every new vessel within a few years now needs to run on something different than oil. So they kind of think in 2050, most vessels are not running on diesel oil. And because vessels have a lifetime of 20, 30 years, it means that most new builds actually also needs to run on something different than fossil fuels. This is from the same report, just showing that today there is 0.5% of the world fleet is not running on fossil fuels. And the order book is around 12% now of new orders. That's last year was not on fossil fuels. Batteries is like 4%, and then it's mostly natural gas. This is quite a nightmare for vessel owners, we find. When we speak, especially with small vessel owners, they have not a large economy. They can't kind of put a lot of money on one solution and risk to lose. So the main question is, what engine do I put on board my vessel? Because it's difficult to change if you choose wrong. And that actually what we see is that, for instance, for offshore wind, there is a lot of vessel demand, but the vessel owners do not finance new vessels because they don't dare to put the money on the wrong ticket. But for us, it's of course very fun because there's a lot of different things to look into, and a lot of things a new techs coming. To kind of make it a little bit simpler to start in one end, this is the kind of our solutions for the Fremtidens Hurtigbåt, which is translated the future of high-speed ferries. It's a Norwegian project where the target is to enable zero-emission high-speed ferries. And I stole this. This is not the slogan of the project, but it's something that I think the project manager said, which I liked. And it's saying that it's never wrong to be energy efficient. So we are not sure which fuel we should choose, but at least let's try to reduce the consumptions. So to kind of glance a little bit on this project. It's owned by most of the ferry operating counties in Norway. So these are the kind of the public counties who charters and arrange for high-speed ferries in Norway. The targets and requirements for the project is to reduce energy consumption by 30%. Vessels shall be running on zero emission, and they should be able to start construction in 2024. Then they have summarized some criteria. So this is a competition that was launched last year, which there were 6 competitors awarded for concept design. But the criteria here was that you have to have a speed of 30 to 40 knots. The range should be 40 to 80, and passenger 150 to 180. There were no requirements for the fuel. but it should be zero emission, or has to be zero emission, I mean. Of these 6, now there are 4 left. This is kind of a glance on them. I think Alan had them in his last news email. What's quite intriguing, I find, is those designs are quite different. Ours is on the bottom right, which is a more classic surface effect ship with 2 side hulls. Then we have SES Europe, which is more like a monohull surface effect ship. LNG Marine has a fully foil-borne, foil-carried vessel. And then you have Transportteknikk with Ola Lille Olsen with more a catamaran, with a foil-assisted catamaran. So quite different technologies on all these 4 of them. But they're also surprisingly similar, which I like. So the speed requirements was 30 to 40, but all ended up with 40. The range was to be 40 to 80, and all of them ended up very close to 40, and all of them are battery powered. So that's the kind of, everybody agreed that these are the kind of things that the high-speed ferry should be. A side note here that wasn't in the press release is that these vessels were ranked, and the ranking number 1 was then ESNA's design. So we got the highest score in the initial competition here. Yeah, so these 4 were awarded then funding to work this year with further development of this design. But to look a little bit on why we ended up with this, everybody liked batteries, for instance. So looking just out on the overall energy efficiency, not the vessel, but the energy efficiency of a vessel for all type of vessels. So yeah, I think there are many paths to zero emission, but a lot of them starts with electric power, just here visualized with a wind farm. So how do you put this electric power on a vessel? You can be battery powered, which gives you very good efficiency. It can give you more than 90% efficiency if you just look at from grid to propeller. So these numbers I put up here is a bit kind of yeah, average. They can be debated, but they are principally in the right ballpark. As an alternative to battery, you can make hydrogen. Hydrogen can be either compressed or liquefied. But the electrolysis here is just visualized with some pressure vessels from Hexagon. Then going from this to the vessel, that's a next debate. You have fuel cells, which gives you some, yeah, typically around 50% efficiency, or you can burn the hydrogen. I don't see any product right now that burns 100% pure. They have some kind of diesel injection, but yeah, those are at least the 2 options. But in principle, if you do that, you are less than half the efficiency of doing it with battery, because you are losing so much on making hydrogen and use on these fuel cells or burning. A different solution is, for instance, ammonia, and you also have hydrogen. You have and create the ammonia. There are ammonia engines coming, but because ammonia burns very slowly, it's difficult to use that in a high-speed combustion engine. So those are more primarily larger vessels. There are then initiatives for fuel cells, but this is not a product that is available at least not in an approved solution. And the efficiency is then even lower, typically compared to hydrogen. But comparing these, the energy efficiency is superior with battery, but you increase the weight and you decrease the range compared to these other solutions. If you just look at the technology, what you can buy, how many suppliers are there approved or not, then battery is very much preferred one. So in a competition for energy efficiency, and if you can solve the range with battery, then that is a very preferred solution. Looking at the high speed, so everybody ended up with 40 knots. There are several reasons for them, and this is one. If you look at routes for passenger ferries, they very often have a main port where they stay most of the time, and then they have smaller stops on a route. So just exemplified here with a port A and B. Then the staple black line here is the actual schedule. So this is an actual route in Norway, and put in the time for that. So this is the staple one, is the actual required schedule to follow, and that is average around 30 knots with the current ferry. So increasing that to 40 knots, if we depart at the same time, we can arrive earlier. We can wait longer and arrive at the same time at the end station. That gives us more time in port B, which we can use to charge the battery. So by increasing the speed of a vessel, we enable more charging. And that is a key element why we are looking at 40 knots, actually to get the electric power. Alternatively to this, charging in port A and B, you can also just charge in one port. If you then go faster, you get more time in that port. So actually the high speed is an enabler for electric commuting. Then looking at the SES, we have a very good energy efficiency, especially low speed with this type of vessel. That gives us more range per battery and also reduces the cost of the vessel because the battery cost reduces. Another item here which we quite like is that if you have batteries with electric motors, if you compare that to a diesel engine, you can take out a lot of power compared to the same weight. So a battery electric motor combo gives you an opportunity to put on a lot more power than you normally could in such a vessel. So you can actually increase the speed even more. Looking then at typically catamaran, which is most high-speed ferries today, and comparing with the SES also have a benefit of that you can carry more weight in a smaller vessel. So then, a catamaran, if you add more displacement, you normally need to make it longer to keep good wave-making properties. But in SES, you can make kind of increase both the width and the length to carry more. You can carry more with your air cushion. Here, so we get the benefit of carrying more with the smaller dimensions. And also, if you look at catamarans and you want to electrify a catamaran, you often get into a bad loop because you add batteries, you add weight. And because you add weight, you need a longer vessel. And because you have a longer vessel, you increase the resistance, and then you need more batteries, and you kind of spiral out of control in dimensions. This is, of course, depending on the range, but a typical challenge with the catamaran is that you kind of spiral out of size control. And I added some kind of some just explanation of the SES, and most of you, of course, know that, but just to exemplify how the vessels we design look like. So catamaran hulls, and we look at the classical fiber reinforced rubber bag at the stern and bow fingers. On the right hand side, a picture here of an SES and looking forward into the bow skirts, and you see the rails where they are attached to the wet deck up on the right here. And then floating off cushion and in transfer section, it looks like this, and then we add the pressure and we partly lifts up out of the water. More detail on this. This is the actual layout of the Sea Puffin 1. So you see the picture of the vessel up on the right hand top corner here. Again, the rubber skirts and the rubber bag. We have a separate fan to pressurize the stern bag. And we have the lift fan, one lift fan, and we found space for that in a kind of a nose structure over the vessel. This layout has enabled us to make very small SES with relatively large fans. So putting a kind of a centralized fan in the middle at the bow here. Looking at resistance-wise of the SES, this is quite interesting when you look at the electric setup. I titled this "Get Above the Hump," which is the main property for get good SES performance. This is calculated resistance, which is quite representative. It's resistance versus speed. And we have the orange line here with the frictional resistance. You have air drag resistance, and we have the wave making. And here we have the hump. So the SES have kind of a sweet spot at around 40 knots. That is actually quite representative for most sizes of the SES. The best fuel efficiency with an SES you typically get from 35 to around 40 knots, which is again a good reason why we want an SES to go 40 knots. Comparing same-sized catamaran with foils and SES, we see the same again. So we have the SES curve, the gray one here, relatively flat but going fast. The catamaran getting high up because of the friction, and the hydrofoil have a lift-off resistance, and then you go quite similar to the SES at higher speeds. So, as I said, we spend much time looking at when does an SES make sense, and then looking at where does the other vessels, where are they better? It's a good way of finding that. So typically, if 20 knots is your speed, that's the kind of catamaran sweet spot if you look at resistance wise, while the SES and the hydrofoil is around 35 to 40 knots. So yeah, looking at then the same, this yellow curve here is the constant power in a motor jet. So if you add if you have the power that gives us around 41 knots in an SES, we typically get 25 to 30% more speed than a catamaran for the same power. This example around 9 knots. But then we had this fun thing about electric vessel. So if you have a diesel engine going from this power and up to this, that adds a lot of weight. It's a significantly larger engine. Using in the electric motors, that could just be a couple of tons or even less. And that kind of is very fun to look at because that can give you very, very high speed. And that's a benefit for the SES because we have this flat curve. You get very high speed, but for a catamaran, it doesn't really give you that much better performance because it's a friction-based speed area. Looking at passenger vessels, this is a very good setup for the operator because this means that if you are running late with the ferry and they want to arrive on time, they can actually increase the speed quite much without using much more energy. So with an electric high-speed ferry, you can actually drive faster without using much more energy if you have electric setup. This is showing the same, but this is measurements from the Steven Pioneer. So this is diesel electric, and this is measured liters and divided with the speed to get you mileage. And it shows you the kind of same setup as this with a flat curve. So for this vessel, if for calm weather, if you go 30 knots or if you go 40 knots, you are actually using the same amount of diesel going A to B. So you're spending more per hour, but total consumption is the same. We have the same numbers with the passenger vessel here. So this is resistance curve versus speed, and this again the mileage versus speed. And here again we see the sweet spot. So going 35 to 40, we spend the least amount of energy. And it's also quite interesting to see that if you go slower, you actually use more. So this vessel is very optimized to go around 40 knots. Another thing with the SES, which hasn't been that much used before, this is the daughter craft again. What's kind of new with this compared to traditional SES is that traditionally the SES have a ride control system to reduce acceleration going at high speed. On this vessel, we also have that, but we are more interested in slow speed motion damping. And the picture here is typical operation in an offshore wind farm where we are pushing on to some cylinders here on the turbine. And we are then activating the air conditioning system to damp the motion. The curve here is measurements on one of these trials. And this is the movement of the bow. So the idea here is that we activate the system to avoid that the bow slides up and down. And if the bow is primarily standing still, it feels safe and you can access the ladder and climb up to the tower. What's also shown here is some trials. So this is a 15-meter vessel. And it has been trialed in Scotland and in Denmark on these 2 wind farms, for instance. In 1.7 meter wave height significant. So this is maximum wave height around 3 meters. And then the slip percentage is the amount of waves where the bow moves more than 30 centimeters, and less than 10 is kind of judged as a acceptable transfer. And these are similar wave height that if you had a catamaran, it should be up to 25 meters to kind of operate and get the same kind of performance as we do in a 15-meter vessel. So that's kind of also the main thing that we are working for with the new techs. And just an illustration on how this looks like. So this is the bodies from Marine Technique. The sea puffin is put on a mothership and illustrated in a wind farm. Looking a little bit more detail on this. This is the physics of it. Upper left is a damper system. So these are the blades that we open and close to control the air cushion pressure. On the bottom here, you see some illustrations on the vessel pushing on to the tower. So this is an offshore wind tower. The fan here is just running all the time at a constant RPM, the lift fan, and supplying air to the cushion. And what we then do when we have a wave through and we lose buoyancy, then we increase the pressure. Then we have dampers on the outlet from the fan, so we add air to the cushion, and we are closing the outlet damper. So increasing the pressure to compensate for the wave through. When you have a wave crest trying to push the vessel up, then we shut off the air supply by one of these damper cassettes on the outlet from the lift fan. And we're having one outlet damper, which we open, so we are taking out the air. This is an automatic system that we are using when pushing on. Some measurements from that, this is especially effective in long waves and beam seas. So this is, of course, when it looks the best. So this is beam seas, and this is accelerations with the vessel just floating and no damping system. And then we have activated the system. This is in 1.5 meter significant wave height, and the sea puffin 1. So these are some of the kind of main benefits and kind of opportunities we see with the SES. Combining this for oil and gas, and we have this collaboration with aircraft vessels. And that is combining the fuel efficiency with offshore operations. So this is very fast, very fuel efficient crew vessel. And we are using the damping system to allow boat landing transfer to offshore installations. Looking at other vessels of similar speed or similar size, you see typically at least 30% reduction of fuel consumption. This is some principle of the electric systems that we are installing. It's a bit mix of all to solve the principle, but it's primarily based around a DC high voltage system. The layout here for the diesel engine is an inline, but here we can also just have a motor and move the diesel engine. But we get power out to the motor and out to the jets. Running this as a hybrid one, we can also have this as a generator providing power to the DC system. On this, you can also power in fuel cells running on hydrogen. You can have gensets. Also, this could be methanol, for instance. We are using this to power the lift fan. So the Seawind Pioneer is fully electric. So that has actually electric lift fans, electric bag fans, electric dampers, all electric SES systems. The bag fan and the damper cassettes, we operate on 400 volt AC. And then we can have battery powered for this as well with a DC fast charging. A kind of an item we see here as well is looking at smaller vessels. If we can find size of motors, size of inverters, etc., that matches what you have on land industry, like in agriculture, railroad, things like that, you can get a lot of equipment, and there is a lot of suppliers coming with equipment from the land industry with kind of smaller power systems. And another project here, we like to look at simulating vessel operations. We have actually developed a tool for offshore wind where we can put in specifics of wind farms. We can put in a vessel and kind of define what is the energy carrying. Is battery, hydrogen, or something different. We can use this also for different vessel platforms, not only SES. Different weather windows, fuel consumptions, and we can then simulate the operation to find out if a specific vessel solves this, and you can look at what size of it becomes and what are the main costs, and how much fuel for it uses. So these are some typical output from that. So this is simulating a hydrogen crude transfer vessel using running on batteries. This is a daily operation. On the top right here, this is the hydrogen content. So this is telling you how much hydrogen you have in your tanks and how it evolves during the day. What we have found for hydrogen as a good solution is a mix of hydrogen with batteries. So these curves here show the energy or power on board the vessel. And the red curve here is showing a small fuel cell installation, which is basically actually running throughout the day. And then the reason why it matches good for offshore wind is that for offshore wind, you have a transit out in the morning. Then most of the day is about idling in the wind farm. And you can then have a total of 10 to 12 hours operation for a day. But most of the time, you're mostly idling. So this vessel is then starting off with charged batteries and fuel cells and using both to get out. And then when in the wind farm, if the batteries are low on charge, it charges batteries, or it turns them off if the batteries are fully charged. Then we have done simulations on this to study, this is a Monte Carlo simulation, adding uncertainty to this number, for instance, weather windows and how many operations they have a day, to get some statistics on this. So this is the result of 10,000 simulations on a 15 nautical miles distance wind farm. It shows that the average transit each day is around 60 nautical miles, and it's up to 90 something. And this is the amount of hydrogen the vessel requires each day. So looking at this, if you go for around 170 kilos, you have enough hydrogen capacity to solve the operation. And this is the basis for that simulation. So this is an offshore wind hydrogen design. This we reviewed and with a hazard last autumn to the IMO IGF code. So to summarize a little bit, as a startup, what we do and what we focus on is figuring out when does it make sense to have an SES. And the summary of that is when we can figure out that it gives the most bang for the buck, or as being more and more important, we get the smallest carbon footprint. So with an SES, if you have an operation where you need to go fast, then it makes a lot of sense. So typically crude files for operation. We have a slogan here with the SES punches above its length. This is about motion damping. So we get a small rotorcraft to operate in wave height similar to a much larger vessel. And this is also if typically, especially for offshore wind, the crude transfer vessels, the typically catamaran vessels, they build them larger mostly than they need to be. And they build them larger because they need this kind of push-on transfer to the wind farm. And they need the vessel to be large to do that in sufficiently high wave height. In an SES, we can do it with the same high wave height, but with a smaller vessel. That is kind of a main motivation to look at offshore wind. And then we have electrification. For an SES, that is very nice because you can remove engines. You can remove gensets actually, but especially we can remove the diesel engines from the lift fan system. So this is from the construction from the Sea Wind Pioneer, and in the nose here, there is the lift fan, and that is electrically powered. Also looking at batteries, electric motors, you can get a lot of power, not so very costly and way heavy compared to diesel versions. So you can get more power and more speed than is the case before. And also with electrification, you can, and also with new sensors for heave damping and methodology for heave damping, you can get better motion damping than what you did before. So kind of these are kind of three main circles of why you could want an SES. So kind of putting on the different some examples designs. We have the daughter craft with the size and the motion damping. Not so much on the high speed and energy efficiency. This is mostly about being small and doing something that a larger vessel otherwise would be required to do. And we are having the hybrid crew transfer vessels, which takes a little bit from electrification, but mostly from the energy efficiency and also from the motion damping. So this is also about getting onto a turbine in larger wave height. We're having the offshore crew transfer vessels, which is primarily about energy efficiency, but also about motion damping to get good access to offshore structures, the motion damping system. We're having the battery-powered high-speed ferry, which is taking a bit of all, and the hydrogen and other zero-emission offshore operation vessels. So with that, I end my presentation. And this was a lot of information. So what I usually say is that if you've forgotten all the other stuff, as long as you remember to buy more SES, I'm very happy with your attendance. Yeah.
Trygve, thank you very much indeed for your presentation. And now I'm going to throw the meeting open for questions and discussion. I have a few myself, but let me first of all look at the chat and see if we have any. No, I don't see any written so far. So if it's okay with everybody attending, yes, please unmute if you wish. I have one question I'd like to raise with Trygve, and perhaps that will spark off some thoughts of others who are attending. And I was quite taken, Trygve, by the represented by the last picture you showed, with this kind of hybrid between battery and hydrogen for an SES, where you're using hydrogen and fuel cells to charge the battery, I take it, during a voyage duration rather than at a terminal, bearing in mind that the concept for the passenger ferry at the moment has a 40 nautical mile, or it's designed for a 40 nautical mile range, presumably using the fuel cell to do to help with the battery charging can expand that range. Perhaps you could tell us a little bit about that.
Yeah, I mean, this is a huge debate, of course. There's we call it a church. Yeah. We like to call it a church. There is an ammonia church, there is a methanol church, there is a hydrogen church, and they are all having extremely good argument for their case. I think my kind of incline to it is, if you can run on batteries, that will always be better, but that gives you, give or take, 1 hour of range. So that's the main drawback. So if you can allow charging, that will give you a good solution. Looking at passenger ferries and hydrogen, there are several initiatives on that. The problem with that is that the energy or power you need is quite constant during your transit. So you go from A to B, and you have a kind of a constant power. So if you need 2 megawatts to maintain your speed, and you need that for 4 hours, then you need 2 megawatt times 4 hours, which is a lot of energy. And if you are doing that, taking some of batteries to do that, you will spend that energy extremely fast. If you do it with hydrogen, you need to supply that energy from the hydrogen or that power continuously. So you need fuel cells that can give you 2 megawatts. If you're looking at fuel cells, they are extremely costly. And if you look at the power a fuel cell gives you, you should run it on 50%. Otherwise, you will, yeah, that's where they are efficient. So that even though the specification tells you that you have 2 megawatts, you basically have 1 megawatt. That gives you a very expensive driveline. So it could be that prices come down, but the main kind of looking at this compared to the passenger vessel, the main thing is that you need the hydrogen power all the time. You can't really benefit from the batteries. What we like with this one is that it just needs much power when going out to the wind farm, and it needs much power when it goes back again, and it needs power when she's pushing on to the towers. So the average power is low, and you're having some peak powers. And the peak powers are great to take with the combination of batteries and hydrogen. That's the kind of key to this. So if you're having, if you're doing a lot of idling, then I think that the battery and hydrogen is a very good solution. But if it's just constant, then fuel cells gets very expensive and very, yeah.
Okay, but it could be a substitute for if you have a vessel going to several stops where you don't have charging at every stop. You can use the hydrogen to do some charging in that intermediate place, which would improve the overall.
That could help.
Yeah. Okay, now I begin to understand it now. Jerome's got a question. How if you unmute Jerome, please.
Yeah. Well, thank you very much. Actually, I know pretty well Trygve's slides, but I do have one comment or something I didn't get. When you say that electric motors are representing additional advantage because of reduced weight, but if we look at the whole, and I will take the example of the RK35, of 5,760 kilowatts. So for 1 hour, we'll need 5.7 megawatt hour. If we consume 1,600 liters of fuel to achieve that, with density of 85, that will represent 1.3 tons of fuel. But the equivalent in batteries to substitute the fuel, even if you reduce the engine weight, if we take into consideration 8 tons per megawatt hour, that is above 45 tons. So how come the electric motor will be an advantage?
Yeah, the electric motor is an advantage, but the battery is a huge disadvantage.
Okay.
No, this is more. This is the same with the kind of summary. Again, if your operation, if you can do it with less than an hour, then batteries adds up quite nicely in weight versus performance and all that. If you go about that, so if you look at the crude transfer vessel and you need 4 or 5 hours of high speed, that is just not feasible. If you look at hydrogen, it's also not feasible. So you're back to diesel today, maybe in the future it's methanol or something else, but right now I think that has to be diesel. But what maybe add a little bit of explanation to myself, but if you have a vessel which is already battery powered and it goes 40 knots, so if you start up with this, can actually be solid batteries, and you are to select your electric motor. If you have a diesel in the world of diesel, you would choose a diesel engine that gives you the speed you need. So you need 40 knots, and so you select a diesel motor that gives you 40 knots. But if in the world of electric, then you have an electric motor that gives you 40 knots. But upgrading that to the engine that gives you 55 knots, it's just a little bit of weight and a little bit of costs, and suddenly you have a completely different vessel. And that's the kind of opportunity with electric motor. But the kind of vessel starting off needs to kind of be able to operate on battery or some kind of electric supply.
Okay, that's clear. Thank you.
Okay. Any questions from the audience? Malcolm, Martin?
Yeah, I have a question. Hello, Trygve. How are you doing?
Hi, Malcolm. Nice to see you.
And you. I noticed in your competition for the Norwegian ferry that of the 4 competitors, you probably have the shallowest draft, with the possible exception of the monohull SES. I'm not sure about that.
Yeah.
I suspect that the passenger application they're looking at, the draft is not an issue, but I do wonder whether your shallow draft is a potential advantage for crew transfer and servicing of offshore wind farms.
Yeah, it's two answers maybe, and yes, there are some advantages on draft. But if you look at offshore wind farms, the main competitors is catamaran, and the draft difference isn't that large actually.
Okay.
And then it's more about harbor operation, and so there are a lot of harbor with draft restrictions. But normally that doesn't give us a huge advantage on. But actually on this competition, it gives us an advantage because there are quite many draft restricted harbors. And there is another one as well, because there are, if you have foils, if you have something coming out underneath the water, that gives you a lot of difficulties in a lot of harbors as well, because there are many of them are very tight, and there are pontoons or things to maneuver around. So having a simple hull with nothing extruding is a quite advantage actually.
Oh, that's an interesting and slightly surprising answer. I thought you were going to say that some wind farms were built in shallow areas. I know we have some in the Thames estuary where there is some advantage, but yeah, I take the point that a conventional catamaran is not that much different.
Yeah, because the wind farm industry has evolved quite much. I think I started working towards the market in 2010, and then it was a lot about performance. And then the main criteria for CTV and vessel developments was to be able to operate in very, very high wave height. So they were looking at 2.5 meters significant wave height, 3 meters significant wave height. That was the kind of targets. But what happens in the last 10 years is that the turbines have become significantly better. So they are much more reliable. So you don't have all that kind of sudden downtime because something is wrong and you have to get out to get it up and running again. You can more plan your maintenance. And primarily when there is bad weather, you produce a lot of power. So you want to keep your turbines on, and you do your maintenance primarily planned, and primarily when there is a little less wind. So the kind of performance requirements has dropped. And then looking at these shallow wind farms, if you can then go out with a shallow and inexpensive catamaran or monohull for that case, and you do have a smaller weather window, but that is often sufficient. So the kind of we started off looking at, as you say, also shallow draft and H and wave height, and thought that could give us a huge advantage, but actually that the focus has shifted from kind of performance advantages to fuel consumption. So all the wind farm owners now, they're asking for low fuel consumption or zero emission and those things. That is become the main criteria.
Interesting. Okay, thank you.
Okay. Could I just ask Jerome a question in respect to these SES, and that is for the services out to the oil and gas installations, which I understand you're interested in. They tend to be a bit farther out than the wind farms. What is the outlook for vessels servicing these?
Well, actually, these vessels are very efficient because the oil fields are very distant from the shore, because they can substitute the use of helicopters for the transfer. So they are very much cost effective, and they are way faster than conventional crew boats. So actually today, whenever there's a crew change, if the crew change is done by helicopter, the helicopter needs to make multiple runs. But they do because they do not transport so many passengers. And we have one model, the ARCAT 35 crew liner, that is designed for 80 passengers. That is 50 knots in max speed when helicopters are in the range of 135 to 140. So they are not quite 3 times faster than us. And they often need to make more than 3 runs to transport the passenger. So overall, we are even faster than a helicopter. And of course, we're also faster than other conventional crew boats that require sometimes the crew change to take place over 2 days with passengers staying in the hotel because they cannot arrive on time enough to catch the plane that departs in the evening. So they are a perfect combination to substitute both the conventional vessels and then the helicopters as well.
Okay, thank you. Yes.
Sorry, Alan, and this is just in terms of time. In terms of fuel efficiency, as Trygve said, it goes anywhere from 30% less fuel consumed to up to 160% fuel consumed, depending on which vessel you compare them to. So so you can have a vessel that is reducing the transit time and that even consumes a lot less fuel.
Okay, I understand. We're talking about, if you like, a different area. Sorry, you've got the hydrogen vessels here, and for helicopters out to offshore, you're talking about fuel consumption and so on right up here. So bringing that down. Yeah, I understand. Yeah, it's interesting. Okay. So, any more for people, or shall I bring this to a close?
I have a question.
Please.
Yes.
Chris, yeah.
So I'm just interested in what is the thrust mechanism? Is this a propeller or a water jet drive that you're using?
We are primarily looking at water jets.
Water jets. And
Yeah.
then we have we have a hovercraft operating in China, which is being carried on a vessel, and the situation is that it's a very tidal area, so that the water goes out and the large vessel is stranded for quite some time until the tide comes back in, and the hovercraft was being used for transportation around during that period. I'm just wondering what happens with this vessel when you have this tidal situation where there's no water, and then the water comes back in. Will this vessel sit on the base, and what happens?
Mostly we look at operations where we don't have that happening, but we have looked at some UK ports actually, where because of the tide difference you can end up stranded. And then this is like an okay solution, because we have I would have to actually show the hull shape if so, but we have the hull shape is a bit it's straight on the inside, and the bow plate is going like that, and then it goes up. So we have kind of a quite strong girders all the way on the keel, and that is the lowest point on the vessels. So if you're stranded, you will actually have a very strong, rigid connection all over that she's sitting on. So structurally and physically, that will be fine. Then the main problem would be more like if you need your if there are seawater systems and systems that can be clogged or things like that.
Any issues with the water jet intake? No,
and we haven't. Not that we have seen. No.
No, if it was sitting on the surface and picking up sand or debris, would this be an issue?
I don't think so. The jets we are using is very strong, rigid or solid steel impellers and kind of quite robust system that are designed to take up debris and kind of things going in there without taking damage. But basically, if you're that low on draft, you don't really operate, and then you will just sit there, and then so it wouldn't be in operation, and then it would be fine.
Just as a thought, gentlemen, with an SES, of course, if the tide comes in and the vessel is then floating, but at very low clearance, when you turn the cushion on, of course, you increase your clearance to the bottom, at least a little bit, I guess. So maybe that would help with avoiding ingestion of sand and so on into your water jet, compared to a catamaran.
Yeah, I think that's what Malcolm touched into. So the on-cushion draft here can be very low. Typically, the high speed or fully on-cushion draft of these vessels is like 0.5 meter. But again, I wouldn't be. I'm not so concerned about the jet itself, because that is a very robust piece of machinery. I would be more concerned about the seawater inlets. So if you don't do anything special with the seawater inlets, they would probably end up clogged. So if you looked at an operation where that is going to happen a lot of times, I would do some special designs on the seawater inlet to be able to back flush them or something to make it more robust.
That's for the cooling of the main engines and so on.
Yeah, typically main engines and electric motors are seawater or water cooled. Actually, a bit surprising problem we found with a hybrid and battery powered vessel is that you need your seawater system running much more than you usually do. So for a normal kind of diesel powered vessel would just turn off all the system at port. But often if you have battery powered, you need cooling or at least ventilation of your battery system. So you need your seawater system to keep running even though at port. And that we found last summer to be a huge problem with jellyfish, actually. Which was we didn't think of that, but that was none of the other vessels had that problem. But it was just because we needed to run cooling while lying at port. So there are some new things when you look at electric vessels that you may have not thought of, at least not us. But again,
Okay.
it's only the seawater system. The water jets are perfectly fine.
Thank you.
Okay. Well, Mike, can I ask you to close us out? You need to demute first.
Fantastic idea, that. Unblock yourself. Yeah, Trygve, thank you very much for that. Very interesting. On the ferries, you're saying that these ferries are doing 40 to 80 nautical miles?
The project requirements was at least 40 and up to 80 nautical miles. That was the target.
Yeah, but have you got vessels that go sort of 100 miles, 120 miles, things like that are battery powered?
Not that we have looked at, no.
Okay, fine.
It's
Battery life and recharging. I mean, okay, you go from one port to 60 miles, you're going to recharge. So you're going to go shut down. What would be the recharging time, bearing in mind that to make money, you've got to keep the things moving?
Yeah, this is a huge effort looking at. It depends very much on your battery type. And so main kind of limit here, main requirement is how fast can your battery charge without being degraded.
Yeah, cooking the batteries, yeah.
Yeah, exactly. And so the kind of typically what we look at is a good charging time is equal to your what you use is equal to your charging. So if you're going from A to B is 1 hour, then charging 1 hour gives you a nice battery profile. But looking at these routes, what we're actually looking at is around 30 minutes to fully charge. So then you are double that, and but then there are not that many batteries to choose from. That is the limit.
So,
But there are the kind of the battery types that are low on weight or comparable low that gives you good charging is typically that if you spend 1 hour of usage, then you can charge it in half an hour.
yeah, I understand all that.
Yeah.
Given all things being equal, that some batteries are better, some aren't, and things like that, what would you expect to be your normal battery life?
Battery.
Battery life, how long would a battery last? I mean, 1 year, 2 years, you got a lot of them to run your ferry.
Yeah, that depends again on the charging time actually. So this is calculated in cycles, and it depends extremely much on how fast you charge. So if you charge in half an hour, as I said, then you get a certain number of cycles until you need to scrap your battery. But if you can double the charging time, you typically get double the operational life of the battery. So that is actually a criteria for selection of your battery, is how fast you want to charge it. What we look at typically on this ferry project is a 10-year lifetime of the ferry or the route. So the contract is typically 10 years. But we don't look at 10 years lifetime, and actually I don't look at lifetime at all. I look at cost of battery per year.
Well, that's what I'm thinking.
Yeah.
You've got a hell of a lot of batteries, even on a 30-meter, 35-meter.
But typically on these, if you look at batteries today, you can typically find something that lasts 5 years. That's a kind of a typically one. If you go, you can find a battery that gives you 10 years. But what you then actually do is that you double or increase the battery size and use less of the battery. So the less you use of the battery, the longer lifetime you get. So you really need to calculate this to find what is the annual cost of the battery versus the operational performance of the vessel to decide on lifetime. There could be that 10 years lifetime is what you want, and you do that by having a larger battery pack. But it could be that you can reduce your battery pack by 40% and only have 5 years lifetime and use actually the same battery. But then you need to replace it twice as often.
And you do this equation bearing in mind that whether you're running a diesel engine, a hydrogen engine, or a hybrid engine.
Yeah, you need to compare
looking
everything.
at that and say, this is going to be the best for what we want to do at the time.
Yeah. So what we are doing here, we have looked at some routes in Norway, and you do your diesel calculations. This is the diesel fuel that you use every year, and adds up to this, and these are the cost and expected cost of that. And then you calculate the same using electric power, and this is your expected electric power costs, and this is the size of vessel and weight will increase a little bit, so you use more. So you need to increase the power or energy use a little bit, and then you compare, and then you need to take your battery cost into that and do the math. So it gets very complex to find a good optimum solution. And then you, of course, you have your weather window, and you have all this, which makes the quite randomized process of actually how much energy you are going to use.
You don't have to run around with deionized water because they're chilled batteries.
And what did you say? Sorry.
You don't have to run around filling the batteries up with deionized water, distilled water, because they're sealed batteries.
Yeah, there are steel batteries. Yeah.
Thank you very much, Trygve, for a very interesting presentation. We look forward to many more, especially from some of the other participants. Thank you very much indeed.
Thank you.
I'll hand it back to Alan now.
I assume that